First, I'll remind you the formula for QB, the BRST charge expanded oscillator. We got Cn L minus N. I'm just writing down the holomorphic part again. There's a corresponding angle. Plus M minus N by 2 Cm Cn B minus N minus N. No, actually no. Minus C0. Okay. We start. We're now wanting me to repeat the last part of the last class. The point is to repeat it, it's not here. Let's wait. Okay. So we have the BRST charge here. And I'll also remind you of the mode expansion of the BC stress tensor. Mode expansion of BC stress tensor. When L0 BC is equal to 2f minus n. Bn C minus n. Minus yes. So this was just sorry. So it went n m0. So sorry. So just minus n. Thank you. Bn C minus n plus minus 1. Okay, excellent. Okay, so in the last class we had begun to try to understand the cohomology of this operator, and we decided to understand the cohomology not on the full Hilbert space, but only on the subset of the Hilbert space that is defined by B0 on side equals 0 and L0 matter plus L0 post minus 1 on side is equal to 0. Okay, this was it was consistent to study the cohomology of the subsector. It was consistent to we looked at the cohomology just on the subset. Sorry, we looked at the cohomology just on the subsector of things obeying this equation. Physical states will obey zero inside. That's not matter. But we looked at the cohomology just on this things obeying this equation. It was consistent to do this because this commuted with the BRST charge, and therefore the action of the BRST charge didn't change the level under this operator. So we had a separate cohomology problem at each value of the level, including level equal to 0. Okay? So we decided to study this cohomology problem. Okay. Now, we also noted that the fact that the BRST charge, okay, we also noted the fact that the BRST charge commuted with L0. It's you see, it's got dimension. The BRST charge went like C times T. So BRST current went like C times T. So it is a dimension 1 current. So the charge was a dimension 0. The dimension 0 charge. And that's basically the fact that for every n it's a minus n. It's the net energy of everything is 0. Okay? Using that, we argued that there was a separate BRST cohomology at every oscillator. Okay? So the full Hilbert space could be labeled by oscillator excitations and zero mode excitations. Okay? The fact that momentum shifts commuted with this BRST charge told us that you could look at the BRST cohomology separately, momentum by momentum. So fix some eigenvalue in the zero mode sector. You look at the cohomology in that sector. Okay? And the fact that this commuted with net oscillator told us that we could look at the BRST cohomology separately, oscillator number by oscillator. Okay? So we've got a separate BRST cohomology problem at every oscillator number. Now at oscillator number 0, the only states in the problem were the oscillator vacuum times the 0. Okay? And then in the last class we demonstrated that the BRST operator just annihilates a general state of this form. The general state meaning a state at every momentum the BRST operator annihilates this. Okay? Notice that the momentum is not completely free because it has to obey k squared by 2 is equal to minus 1. Right? Because it has to obey this condition. Because we're at oscillator number 0, this part was 0. Because we're at oscillator number 0, this part was just simply alpha prime k squared by 4. So it's not completely free, but that condition is completely determined because we've got a whole shell that obeys alpha prime k squared. It could be anywhere on the shell. All of those states were annihilated by the BRST charge. Was that part clear? Or now we were saying something was not clear. Was that clear? No. Okay, there was some algebra that gave us, but this annihilated first. Okay? Now, the algebra that annihilates that state tells us two things. Firstly, it tells us that every state at oscillator number 0, obeying the Marshall condition, is BRST closed. Secondly, it tells us that no states at oscillator number 0 are BRST exact. Okay? So all oscillator states that obey the Marshall condition are closed and form inequivalent conjugacy classes of the BRST.
None of these states are exact.
None of these states are exact because we've seen that a BRST charge does not change oscillator. Okay? So, because the BRST charge does not change oscillator, if you had an exact state at oscillator number 0, it has to be Q BRST acting on a state at oscillator number 0. But we've seen that Q BRST annihilates all states at oscillator number 0. Therefore, there is no exact state at oscillator number 0. Okay? So every state at oscillator number 0 is physical, and no two states are equivalent to each other. Clear? Okay? So each state is its own physical cohomology class at oscillator number 0. Of course, there aren't too many states, they're just labeled by the momentum. These states are, of course, the tachyon. Okay? So this is a bit of a depressing result. The tachyon is not thrown away by a fancy BRST, blah blah blah. Because it couldn't have been, because in the second lecture or so, of course, we found it was a tachyon. It was not as rigorous as what we're doing now, it was pretty good. So we should find a different result. But anyway, it's not like this fancy stuff allows us to get rid of the tachyon. Okay, so far so good. Now next, we went to oscillator number 1. Now, I want to emphasize I'm doing it holomorphic sector. I'm doing it only in the holomorphic sector. It's exactly the same thing going on in the anti-holomorphic sector. The full spectrum is a product of it. Okay? But just because in the algebra simple, I work only in the holomorphic sector. Okay, so in the last class we wrote down the most general state at oscillator number minus 1. Sorry, number 1. It was E dot alpha minus 1 plus eta B plus gamma C. I may have used different symbols for these coefficients, for which I apologize. Okay. Acting on K. Now, what can you say about K squared? Because we're oscillating number minus 1. Oscillating number 1. K squared is equal to 0. Right? Oscillator number 1, the Marshall condition, this condition, just tells you, because the oscillator number exhausts this one, eats up this 1. Everything else has to be 0, but everything else was just alpha prime by 4 K squared. So K squared is 0. Okay? So it's an arbitrary K, except that we know that K squared is 0. It's arbitrary, null momentum. 26-dimensional vector, that's null. This is the most general state. Okay? Now what we want to do is to get what we get when we reacted to the BRS state. Okay? So I'll quickly go through the algebra we went through last time again. Okay. So reactant side, QBRS side. Now, let's look at this carefully. So I've written down the formula for QBRST on the top, expanded in oscillators. Okay? Yeah. So let's look at this carefully. Firstly, let's look at what happens. When we act with this term on any of these lines. Okay? I'll just go through it. Because Polynomial said he was very confused. Okay. Okay. So let's take this guy and act on this. How will we get something non-zero? You see, because one of these two, there are two ways to get something non-zero. Either we take C0 and L, so we take n equals 0. That gives us something non-zero. Why does it give us something non-zero? It gives us something non-zero. It gives us something non-zero because L0 acting on this state. Actually, in this case. Anyway, yeah, it gives us something non-zero because L0 acting on this state is not necessarily 0. Okay? Actually, in this case, it is 0 because. Okay, but this argument will be general for every level. So that it will give you L0 acting on the state. Okay? And C0 acting on the state. Neither C0 nor L0 in general annihilates states of this form. Okay? But, so what will it give you? It will give you L0 acting on the state, which is some number acting on the state. Okay? It will give you L0 acting on the state. The state has a particular number from the Marshall condition. Okay? And it also gives you, so it gives you L0 acting on the state, but there is another object here which is C0 acting on the same state. The C0 just goes through this, and this vacuum state that we started with, this K was annihilated by B0, not annihilated by C0. So it's just there. Okay? Both these states are there, okay, and they're proportional to C0. We'll keep them aside. So we get a term that is C0 times L0 matter minus 1 acting on this E dot alpha minus 1. Okay? Acting on the E dot alpha. Acting on 0. We'll keep this aside. We will see at the end that all states that you get that are proportional to C0 will cancel because of this condition of the states.
Why is it 0?
Okay. All I'm doing is taking this term, adding this term, acting on it. What I will show you is that all such states will in the end cancel. Here we can see the cancellation quite easily actually, but we'll do it more, an abstract way so you can see that's working. Okay, all such states will just cancel. Anything that we get proportional to C0 will just select and keep, and in the end they'll all end up cancel. Okay, so there's the C0 nonsense that's not going to play any role. But then there was also a term that was L minus 1. Sorry, L plus 1 times C minus 1. Okay? What do you get when you act with L plus 1 and C minus 1? The L plus 1 has a piece that is alpha 0, alpha 1. Okay? That's the only piece that will give something non-zero. Because there is an alpha 1, but that will be killed by contracting with alpha minus 1. All other pieces would have like an alpha 2 and alpha 3. We'll just go through and kill our k. So the only part of L0, L plus 1 that will contribute is the alpha 0, alpha 1. Is this clear? Okay. Now, alpha 0 was dotted with alpha 1. L0 was like alpha 0 mu, alpha 1 mu. In space time, these indices were dotted with each other. This guy, the alpha 1 contracts away with this guy. What happens to the vector indices? This E takes the role of the alpha 1. Okay? So what's left behind when we do this is you see that you get C minus 1 E dot alpha 0, which is the same thing after proportionality factor as E dot k, because alpha 0 was the point. So E dot k C minus 1 on k. Now that's what you get from this guy acting on this state. Okay? We've kept that C0 thing up there. We collect all the C0 debris. They're all cancelled. They're not important. But this term is not cancelled by anything. It's there. It's physical. Clear? Okay. Now let's look. So we dealt with. You could ask, what about this term? This term acting on this term. You could ask, well, look, firstly, what about m equals n equals 0? That is 0 because C0 squared is 0. No such term. Okay, so all zeros aren't allowed, that there has to be at least one positive guy. Because it's normal ordered, the positive guy is on the right. That kills the state. Okay? So this term can only contribute if it hits some ghost creation operator. Okay, this term has no ghost creation operator. So this term acting on it just gives 0. So we've accounted for all terms acting on this state. Okay? So all terms acting on this state give us this plus some C0 stuff. Is this clear? Sorry, it's not clear. Okay. Now let's do the same with the next guy. Let's do it on this guy. Okay. This was. Okay. Let's look at this term acting on this. What can we get? Firstly, there's going to be some C0 stuff. Okay? We'll deal with that in just 1 minute. Because the C0, L0 acting on this. It's just the same actually. Right? This will be C0 E dot alpha minus 1 plus beta. Is this clear?
Why not the last term?
Last term also. I'm just doing it better. Okay, actually this will not be the only kind of thing that's there, because stuff from here will also contribute to C0 piece. So hang on for a moment. Okay, but your main focus should not be on the C0 pieces. Should be on everything else. Okay, what else do you get? The thing that's not C0. Well, what you can get is from C1. Exactly. C1 can kill B minus 1. What's left is an L minus 1. Now, what term in L minus 1 does not annihilate K? The term in L minus 1 that does not annihilate K is alpha minus 1 dot alpha 0. Alpha 0 is K. Okay. So, what we will get is beta alpha minus 1 mu K mu. There's actually a proportionality factor, but the same proportionality factor between these two terms. So we won't bother. Is this clear? Okay. Now what remains is stuff that you get from this guy acting on this guy. Okay. So see, if you want to get something non-trivial, you better have a C1. Okay? So what you're going to get is C1, C0 times B minus 1. The C1 will annihilate the B minus 1. Okay? What will be left over is C0 times B minus 1. Okay? So that will add up in the action here. Now, let me tell you how this is going to work. Let me just explain how this is going to work. So you see this pattern. You see L0 matter minus 1 on this state times K is equal to 0. Why did you know that? It's because that state obeyed the condition L0 matter plus L0 coast minus 1 was equal to 0. That's how we determine K. That was the condition. Yes. But this state has no post excitation. Okay? So the L0 coast is not playing any role. Okay? So this thing by itself annihilates that state. However, that same argument does not work here. Why? It's because L0 coast does not annihilate that state. So what we should, if it's going to turn out to be 0, we should get an extra contribution here that will be precisely L0 coast acting on the state. Okay? And this extra contribution here basically is that. So what we get is a term proportional to B minus 1 to C0 with an extra series C0 and a factor of 1. I'll leave you figure out that number. That's exactly what you will get by acting on the state with L0 coast. Okay? So the C0 term acting on the B minus 1 will also give you 0.
Due to the extra term generated.
Due to the extra term generated. Is this clear? Yeah. See, we know that all these states are annihilated by L0 matter plus L0 coast minus 1. We know that, right? Okay? So, if whatever comes here as the coefficient of C0 is L0 matter plus L0 coast minus 1, we just get 0. For the first term, we've seen that happens, just because the first term doesn't carry any L0 coast. Okay? For the second term, I'm claiming that also happens. The extra term comes from this piece acting on this. You see, you get something proportional to C0 times B minus 1 times beta. And it's a matter of algebra that I won't try to get straight here to get the right number. Okay? This happens with all terms. The term proportional to C0 is always proportional to the term proportional to C0 is always proportional to this additional stuff. This L0 matter plus L0 coast minus 1. In fact, we could probably argue that on very general. It's probably from some OP. Let me see maybe in a minute to give you the structure. Okay, I'm almost sure one could, if you spend 5 minutes, you would be able to find some nice OP type argument that establishes this. But the part of the state proportional to C0, okay, is proportional to this. It will come from the OP of B0 with JBRS, whose pole part is this term. Okay, but I would try to get that straight. Fly. Okay. This always happens. Okay. Again, the important thing is not this part, which is just going to go away. Okay? But this term, and we found it. Okay? What about the term acting on the C? Okay? So let's see. Anything from here? Well, you get C0, L0. Same story. I'm not going to talk with the C0 term. Okay? Anything non-C0? No. What about this term? What about this term? Well, that's clearly a C0 term. Oh, what about this term? Well, we could try to get B1. We get C minus 1, but then what has to be left over? A C0. It gives you something, but it's the stuff that we combine together to give you C0 plus times L0 plus L0 cos minus 1. So in fact, this term is just annihilated by the big RST. Everything is C0, and I think we will check that the coefficient of that C0 is just C. Is this clear? Okay, so our net result is that QBRST on psi is equal to beta alpha minus 1 mu k mu plus E dot k C minus 1. Is the result clear? Any questions, anyone? Okay, so now we're going to actually use this. We're going to use this to determine the cohomology at level. Okay. Firstly, if we want to be, all states of cohomology are annihilated by psi. Suppose we took a state of this form, we've acted with Q on it, we got that, it's not zero. In order for it to be zero, what conditions must be obeyed? Beta is equal to 0 and E dot K is equal to 0. So a state is annihilated by the BRST charge. A state of this form is annihilated by the BRST charge if and only if beta is equal to 0 and E dot K is equal to 0. Is this clear? Just because beta multiplies a non-zero state. That's what it means to be annihilated. Is this clear? Now, the next question we can ask is, where is the state? So, what?
Yeah, what can the oscillator be proposed? Alpha dot k alpha minus 1 mu k mu equals to 0.
Alpha minus 1, because alpha minus 1 mu is an operator. You say, what does it mean? Why can't the oscillator be? There is an alpha, there is an operator for every mu. So this is an operator, is just non-zero. And that is actually non-state, produces some non-zero state. Okay? These are numbers, so they can be zero. You have to put some condition on operator. It is what it is. Is this clear? Okay, excellent. Okay, so in order for the state to be BRST closed, it has to obey these conditions. Okay, now That means which states are BRST closed? Let's review. E dot alpha minus 1 plus gamma c minus 1 on psi equals 0 are closed provided E dot k is 0. Is this clear? Okay. Now, the next question is when are states exact? Because everything is level by level. Right. So, because things are level by level, anything that appears on the right hand side of this is exact. Okay? So, C minus 1 on K with any coefficient, because we can arrange by choosing E appropriately, we can arrange any number here. C minus 1 on K with any coefficient is there. So, what are the exact states? There. C minus 1 on K, spanned by C minus 1 on K, and K dot alpha minus 1. K dot alpha minus 1. Okay. These are the basis of exact states.
Beta equal to 0, E dot k equal to 0 are condition on the physical state.
Yes, the condition on the state so that Q on that state is 0. And now we're going to ask when can such a state be obtained by acting Q on some other state?
So psi is any general state you're taking.
What?
Psi, any general state you will start with.
Yeah, good.
It's not any BRST closed or something like that.
Exactly. If we start with the BRST closed state, then acting Q1 will get 0. The question you're asking is, look, see, we know a cheap way of producing BRST closed states. Take Q, act on anything, something that's not BRST closed. Then that is automatically BRST closed, because Q square is equal to 0. So, in this list, this impressive list of BRST closed states, some are non-trivially closed and some are cheaply closed, because they just Q on something else. So we want to get rid of that trivial part. So which of these states were closed because they were Q on something else? See, anything that is exact is automatically closed. So when we look at the state of space of exact states, it should be a subset of the space of closed states. And what we found is spanned by C minus 1 on K and K dot alpha minus 1 on K is BRST exact.
So it's one thing that the state that you have written on the left hand side is BRST closed.
Which one? This one?
E alpha minus 1 plus.
Yes, this is BRST closed.
This is BRST closed. Okay, so you get the condition on any general state psi which has this expansion.
Yeah.
And then.
So most general state is this. For it to be BRST closed is this.
So these two are the additional conditions that we will get.
Now I want to know of these states which are BRST exact. I can go between these states. Sometimes differences between two of these states are differences by a BRST exact state. Okay? Exactly. So difference that will automatically be closed. But as we have discussed in great detail, such differences are physically trivial. Two states that differ by a BRST exact state should be treated as physically identical. Okay? So I want to know what generates this BRST triviality. Is this clear? And what we've seen is that two states that differ either by C minus 1 on K or by K dot alpha minus 1 on K differ by a BRST exact state. Okay? So, this gamma parameter is entirely exact. It's entirely unphysical within cohomology. We can set gamma to any value we want within cohomology, in particular to 0. Moreover, remember we had as our states all those states which were E dot alpha minus 1 such that E dot K is equal to 0.
So that will never be satisfied.
Wait, no. What about choosing E equals K? That's this.
It's the second statement.
You see, E was an arbitrary polarization. Okay? All polarizations that were orthogonal to K were physical. Okay? Now what we are saying here is that polarization chosen to be equal to K is exact. And you might say what I think Mangesh tried to say.
K square is 0. So
You might say what Mangesh first tried to say, well, we don't have to worry about that then because anyway it has to be orthogonal to K, so it can't be equal to K, so why worry? Except that remember at this level K square was equal to 0. So K is orthogonal to K. So one solution of the physical condition was E is equal to K. That solution is BRST exactly. Is this clear? Is this clear? Okay? So, the polarizations orthogonal to K are physical, and any change in polarization proportional to K is trivial. Exactly. Now, Orram was hinted when he asked, what do you mean is trivial? But what do you mean? I mean, from the point of view of low energy physics, what does it mean is trivial? The point is, it's gauge equivalent. Okay, by taking half of the string, we're essentially dealing with the Engel's theory. If I doubled it up, I would deal with Einstein. But this gauge condition here, this condition that this E is the polarization then of the gauge field. The fact that A is the same as that if you take a polarization and shift it by K, okay, you take that polarization and shift it by K, it doesn't change any physics. It's basically the U1 symmetry of gauge theory. A mu equal to A mu plus L mu chi gives you the same A mu. You go to momentum space, this tells you A mu is proportional to K mu. That change does nothing. So you see this BRST business, we're now getting a physical understanding of it. The requirement that your BRST closes is just a requirement. Okay? The requirement that the statement that BRST exact things give you the same scattering amplitudes is the statement that in a gauge theory, if you change gauge, you'll get the same answer. That's the low energy manifestation of this. Okay? So now that we understand this, let's first do some counting. Please.
Why do you say it's low energy?
I'm saying it's low energy manifestation because we have a separate low energy understanding of this massless sector, which is that of Einstein gravity. We know that it has a gauge variance. Because I'm dealing with half, just the left movers and right movers, I'm cheating and dealing with gauge theory. But there we understand why some gauge fields and other gauge fields give you the same answer from a familiar low energy point of view, namely Maxwell gauge variance. We need to double up Einstein gauge variance. Okay? Notice, by the way, an interesting thing. String theory scattering amplitudes are automatically computed in Lorentz gauge. Because E dot K was equal to 0. That's the gauge condition from the low energy point of view. Del mu mu equals 0. It's a very strange thing. But this whole procedure, the gauge fixing procedure we used for string theory, from the low energy point of view, automatically put us in this gauge. That's not surprising. Okay? Because this is basically the only Lorentz invariant gauge condition that there is. We were quite careful to preserve Lorentz invariance. But it's an interesting fact that one should keep note of. That if you try to make contact with the low energy point of view, you're forced to work in a particular gauge. More precisely, the polarization vectors are forced to satisfy this. String theory automatically has polarization vectors that satisfy this condition.
We are supposed to be never chosen a particular gauge.
Well, we chose a gauge right at the beginning. We chose a conformal gauge. We had a big gauge invariance on the world sheet and we fixed it somehow. Well, that has some low energy manifestation. This BRS is an entry of that gauge fixing. So we've done a lot of gauge fixing. Okay, yeah, it might be it might be nice to understand this better. Here I'm just saying it from observation, experiment.
This is something like the manifestation of Q exact states.
This is the Q exact states. But this was just a physical state condition. String theory is working with a particular convention. Is this clear? And this here was actually the unfixed gauge invariance of Lorentz gauge. Because once you go to Lorentz gauge, you can continue to make such gauge transformation provided k square is equal to 0. That's exactly the kind of thing. Because k square is 0 and everything. Okay? So string theory, so it's like this. It's like our gauge fixing procedure on the world sheet string has partially fixed gauge. Sort of like going to Lorentz gauge. But there is some remaining unfixed gauge invariance that is showing up in the real. Is this clear? Okay. Very good. So now, just to end this, let's do some counting. What is the dimensionality of the cohomology? What's the dimensionality of the cohomology at level 1? Somebody there. Hilbert space up to Q. What is the dimensionality of the Q closed Hilbert space at level 1 modulo states that are BRSC exact? Some numbers. Like 1, 2, 3, 4, 26, 48. What's the answer? Come on, what was the dimensionality of level 1 before we put any condition? 26 plus 2, exactly 28. That's right, because you could have 26 states by the matter oscillators, one state from the C oscillator, one state from the B oscillator. Okay, so it was 28 dimensional states. I'm fixing a particular K. Nice finite area. Now, what is the dimensionality of the cohomology?
C is gone and 1 so 24. You see, we killed 2 by these 2 conditions and killed 2 more by these 2 equivalences. Okay? Now let's see how it worked. You see, we had 26 oscillators. We added 2 more because we added the ghost states. So, of course, we have to kill 2 because we added these 2 completely unphysical ghost states. So we end up killing 2 more to go just down to 24. Now, where do we see 24 before? Little group of a massless field. Or we saw it in our light code gauge quantization of the string, where the number of oscillators was 24. Because there were just 24 oscillators at level 1, how many states should there have been that are physical? 24. Because each of these 24 oscillators could act with alpha minus 1 in the vacuum. We knew that the correct answer was 24. The transverse oscillators of the string. Okay? And we're getting this out of this BRST procedure. Okay? I'm going to explain to you now, soon, that this works at every level. And at every level, what we got is this huge monster. Right? So the Hilbert space produced by acting on 28 oscillators. But then we have BRST, the BRST procedure. The BRST procedure just kills things coming from two of those oscillators and then removes the degrees of freedom of two more by exact explanations. Okay? So when we actually do string theory calculations, as you will see, we work within this BRST framework. Okay? Great. Now, before proceeding to the general argument, there's one thing I wanted you to know, wanted to help you understand. That's the inner product of the space of states. Okay, so let's look at the inner product on the space of general states. Suppose we have E dot alpha minus 1 plus beta B plus gamma C and psi, and I take the K. This is the psi. And I take the inner product of psi with itself. Okay, what do I get? Well, so this psi is equal to K with E dot alpha 1 plus E star, beta star, E is probably E3. Okay, you can take the character, E star. Okay, well, plus beta star B, so B1 plus gamma star. That's clear? You're familiar with the fact that Hermitian conjugation on an operator flips n to minus n. Where does that come from, by the way? Can somebody remind me? What? Reality conditions. And the reality conditions in Lorentzian space, when tracked through down to Euclidean space, then from the map from cylinder to the plane, imply this. You know that, right? Okay. So, great. So now we take this side with this side, we take the inner product. What do we get? Clearly we get E star dot E plus beta star times gamma plus gamma star times beta. Okay, so this is E star dot E plus beta star plus gamma star into beta plus gamma. Into yeah. Let's say the temperature will be some positive, some point. Yeah. Minus beta star plus gamma star into beta minus gamma all divided by 2. Just because the terms that are beta star beta and gamma star gamma cancel between those two, and the remaining terms, the beta star gamma and gamma star beta, don't cancel, but they give you exactly what you want. Okay. Now, to make this really clear, let's expand this. This is a sum of a space and time. In space, we get EI star EI. But in time, we get minus E0 star E0. And then we have plus beta. Okay. So what is the signature of the inner product in the space? So this is a 28-dimensional space. What's the signature of the inner product?
But didn't you already Euclideanize?
Didn't we already but we're using inner product, which is okay. You see, if we literally Euclideanized, k square equals 0 has no solutions. So we do the Euclidean calculation and then analytically continue the answers back to the place where we really want the answer, in Lorentz space. Okay? In order to talk about physical states, it's very important to be in Lorentz space. See, because del square phi equals 0 has plenty of solutions in Lorentz space, but there's no solutions that don't blow up at infinity in Euclidean space. So no solutions of not only the solutions of the equations of motion of the Euclidean theory in general. Not to propagate it. That's what we got on. Yeah. So we've gone back to Lorentz space. Okay? So you should think of Euclidean space as a way of getting answers, which then you analytically continue back. Okay, that's it. Now, what is the signature? What's the signature of this inner product? It's 28-dimensional space. What's the signature of the inner product matrix? It's 26, 2. This is 25, and this one gives you a positive. No? Whereas this one and this one give you negative. So, another way of saying it is that we can choose a basis of states in the space in which 26 of the states have an orthogonal basis in the space, such that 26 of the orthonormal vectors have norm 1, but the other two have norm -1. The fact that we've got the not of positive definite inner product on our space came A from the fact that we had 0 and B from the fact that we were dealing with coasts. There's some expected thing, right? We've got the Hilbert space enlarged to include coasts and without removing the gauge invariant states, now expected to be unitary. Okay? Now let's look at, so this is for general states. Now let's look at those states that are Q-exact. Sorry, Q-closed. Okay? So, those states that are Q-closed, we still have this general inner product except there's no beta term here. Okay? Since there's no beta term, this part is just 0. So the inner product is just star dot E. Okay? Now E is restricted so that it's orthogonal to K. Now the full space of things that are orthogonal to K are made up of K plus positive norm states or positive norm E's. So the 24 positive norm. So now in this inner product restricted to the class of physical states, the signature is actually 24, 0, 0. Do you see? That, so the basis of states are those that are E dot K is equal to 0 and orthogonal to, if you choose K to be, suppose I choose K to be 1, 1, 0, 0, 0. This is dimensions. First component space. Okay? Anything in this part is orthogonal to K. And 1, 1 is also orthogonal to K. All of these clearly have positive number. Because they have nothing to do with time. Okay? This guy clearly has 0 norm. Because it's E dot E which is K dot K, which is 0. It's null vector. And this guy, the remaining one, which was the gamma, also has 0 norm. Because unless there's a beta in an expression, we just get 0. Alright? So the set of physical states has a 26-dimensional basis. Okay? 24 of these basis vectors, positive norm. 2 of these basis vectors have 0 norm. There are no more negative norm states left. But there are zero norm states left. Sort of interesting, right? Now, both the zero norm states are BRST exact. Because precisely those states were zero norm. That were BRST exact. Which were the zero norm states? A, this gamma C minus 1. And B, E proportional to K. It's precisely the gamma was zero norm because it just didn't enter the inner product. And E proportional to K is zero norm because K dot K is zero. Okay? Why are BRST states, BRST exact states always zero? Very serious. Because suppose you've got some state psi, which is Q times chi. Then such a state is orthogonal to every BRST closed state. Because suppose zeta is BRST closed, then zeta Q chi is equal to Q zeta chi, which is 0 because zeta was BRST closed. And using the fact that Q is a Hermitian of. Yeah, I'm saying that any BRST exact state is orthogonal to every BRST closed state.
That's where we had this formula.
Exactly, that's where it came from. Okay? But in particular, then it's orthogonal to itself. Because a BRST exact state is in particular BRST closed. So any BRST exact state is automatically null. Okay? In fact, it's even simpler. You could just take the norm of this, right? If you get Q squared, if you're just interested in the norm itself, Q squared, chi, which is 0 because Q squared is 0. Okay? So we knew on general grounds that the states that were BRST exact had better be zero norm states. Because they were the unphysical things. The unphysical thing was the set of those states whose dot product with all physical states was 0. In particular, those states whose dot product with themselves is 0. Where the word physical is used for BRST closed. That's often the way. I'm not sure how universal the terminology is, but it's convenient to call states that are BRST closed physical and states that are BRST exact pure gauge. Okay? So pure gauge states are orthogonal to all physical states, including themselves. Okay? So that would be another way to figure out which states are BRST exact. We're just looking at state of BRST closed states and then finding those that have zero. Okay? Now, on BRST cohomology, we have a positive definite inner product. Right? Because, and a well-defined inner product. Because, suppose I've got some state. Suppose I've got some state A. Say I've got a state A, and I change it by a BRST. Sure. A plus Q and B. Then the dot product of this state with any other Q closed state is independent of B. Just because Q and B is orthogonal to every Q closed state. Okay? So, we've got now an inner product on the space of BRST cohomology classes, which is well defined because it doesn't depend on which representative you pick, and it's positive definite. The only time that you get 0 in this inner product is if you're in the cohomology class of 0. Okay? So on the space of cohomology classes, we have a nice well-defined inner product, positive definite inner product, And this will be at the heart of the consistency of the probabilistic interpretation of string theory S matrices. Because we will associate physical particles with classes of realistic cohomology. And though the inner product is crazy and has all these negative things in general thing, and the space of realistic cohomology, we've got a nice positive definite inner product. Well suited for the probabilistic interpretation of quantum mechanics. Okay, I've been through this very slowly, just so that every concept is clear. What is this all clear? Any questions or comments? Questions, comments? Okay? So very well, happy. We're now going to go on. I'm now going to go on to outline a formal proof of the no-cost theorem. The no-cost theorem is a theorem, well, at this level.
In this slide, so what happened with the tachyon states?
The tachyon state, there was nothing to say about them. You know, all states were Q closed. None of them were Q exact. They're there. BRSC has nothing to say about them.
Is that a problem?
It's a problem, except that it's a problem. But we knew we had this problem right at the beginning of the line code. And the attitude is always going to be the following. The first few lectures of this course are going to be dealing with the baby theory, even though it has a problem, because we know how to fix it. We fix it by moving to the superstring. The superstring has no tachyon. However, as you already see, the study of string theory, perturbative string theory, has a regrettable amount of technical sophistication. And the degree of technical sophistication gets squared, with roughly speaking, when you start looking at the superstring. As those of you who attended Ashok's talk might have noticed. Okay, so our attitude is following Polchinski to use the existence of the bosonic string, which as far as we know is physical curiosity, as a pedagogical stepping stone. Okay, every technical complication that exists in the bosonic string will exist in the superstring, but the converse will not be true. Okay, so we will use the existence of the bosonic string to separate issues. Okay, so this thing has a tachyon, it's true. Now, tachyon is not a death knell for a theory. Because a tachyon just tells you you're expanding about an unstable vacuum. Now, there is a stable vacuum, you might have zeroed in on the correct thing. So what I mean is that it's possible for a theory to be tachyonic and yet to be entirely consistent. It's just expanding around an unstable vacuum. Doesn't tell you that the theory is a single one. However, the theory is not unitary, for instance. It's not a question of expanding around the bad vacuum, it's just dead wrong. Okay? So, even though the bosonic string is unstable, we can understand a lot about string theory by studying it, because it must be as consistent in a deep sense as all the other things. Okay? Of course, it's not very useful because you actually start restructuring about this theory and you roll down the hill. It's not a useful model of physics, but it's a useful training ground to try to find useful models. That's our attitude. Okay, so we will discuss the superstring, but you'll have to wait for it. Okay, some people who teach this course would directly jump into the superstring. That might also work, but it would really. I assure you, if you think what we're doing now is technically complicated. Have you read the story by Kafka? It's called The Castle. This guy goes to a castle, he's sent on some mission, and there's a doorkeeper who won't let him in. Through the book, he's just at the door. It's a big book and he's always just at the door. But anyway, he's reasoning with the doorkeeper at the time. And the doorkeeper says, look, it won't help you because If I let you give me the next doorkeeper, he's thrice as big as me. Okay.
So for now, tachyons are physical in the cohomology sense, but not physical.
So they will enter as matrix calculation.
They will enter as matrix calculations. In particular, when we actually start computing S matrices, the first S matrix we will compute is 4 tachyons scattering. Just because we won't have to deal with the indices of the gravitation. And when we do 4 graviton scattering, the tachyon, they will enter as poles in various S matrices, not just themselves. They're there. This is a theory that I have a tachyon, what to do. Okay? But we will graduate at some point to studying a theory that doesn't. Our study of this toy model will prove very useful for that purpose. Okay, great. Okay. Fine. Any other questions or comments?
This removal of two of these to getting two null is something related to that choosing this vector being null like 1 0 0 0 1, and since this dot product is this vector will be only getting confused about this
Why 2? 2 was the same as the number of BRST exactions. That's the same 2. Now, why did you know you had to get 2 null? You see, as you've seen, there's a direct pairing between number of closed and number of exact states. So, at any given level, number of non-closed. Suppose you've got a state that is not closed. It also leads to a state that is exact. Right? Because Q acting on that is something. Okay? So at any given level, there's always a pairing for every state that is not closed, there is a corresponding exact state. So since the counting had to be 28 goes to 24, it had to be that we got 2 states that were not closed and 2 states that were exact. Now, was that your question? I'm not sure if I'm answering your question. Okay? You could ask, what is, from the low energy point of view, where did you see 2 such states? And that's sort of interesting. Suppose you did an BRST quantization of Yankel's theory. In fact, maybe we did this in my quantity theory course. Okay. Suppose you did a BRST quantization of Yankel's theory, or the Maxwell theory. You go through a very similar BRST procedure. When there is C coast and E coast, you go through a very similar discussion of BRST cohomology. And you will find exactly what we got at level 1 of the string. Namely, you will find things that are created by C oscillators. Nothing created by B oscillators. Okay? And you will find the stuff. The close condition will tell you that. Basically, you find this stuff. So, what I'm trying to say is that the 2 null states in string theory are identified with the 2 null states in the BRST quantization of Yankel's theory. Okay, so if you just did the BRST quantization of just the Maxwell theory, okay, you'll find 2 null states there. One of which is the pure gauge action on A, and the second of which, the Maxwell theory in the gauge del dot A. BRST quantized Maxwell theory in the gauge del dot A. One of this will be the states that are pure gauge with k square equals 0, and the second of which will be the C coast. This is directly that. By the way, one more comment before we go on to the general. But one more comment before we go on to the general proof. Suppose we did this at higher and higher levels. You see, at each level we'll see a lot of states that are not Q closed, but an equal number of states that are Q exact. If we take this lesson seriously of associating states that are Q exact with gauge invariances, what this suggests is that string theory is a theory with a huge number of gauge symmetries. Those at the massless level are those that are familiar to us. the Einstein, Maxwell region. Those at higher levels are not familiar to us. Okay? This has been said from the early days of string theory. Nobody has yet managed to make it really interesting, into an interesting precise way. With sort of standardizing statement that seems to be built into the formalism string. Very large gauge invariance that allows you to take full set of 28 oscillators, 1 plus 1 dimensional field theories, and convert that to 24 1 plus 1 dimensional. Sounds interesting. Yeah, nobody's made that interesting.
Gauge invariance is again low energy.
Well, you see, it's hard to say low energy after this because zero energy is separated from all other energies by Pascal. But oscillator 1 and oscillator 2, the energy at oscillator number 2 is square root 2 times the energy at oscillator number 1. So hard to say low energy, I mean low energy compared to what. But what I mean from space-time point of view. From a space-time viewpoint, it looks like there's an infinite amount of
Those levels are massive.
those levels are massive, really.
And they have a gauge invariance.
They have a gauge invariance. It feels like the gauge symmetry is Higgs. Yeah. But as I say, nobody's made this mistake.
So out of the states at any level, can we say with certainty that all will have polarizations orthogonal to?
All will have polarizations orthogonal to it. We can say, I'm going to prove this, but we can say that there's always a choice of BRS techniques in which BRS representation. Okay, so let's move on to the more general analysis. Okay, what I want to show is that at every level, the set of BRST cohomologies is isomorphic to what you would get by light cone quantization at that level. Okay, that is the aim. And quite remarkably, quite remarkably, you can actually prove this. Okay, so we're going to prove.
So Logos theorem is what you would say.
Yeah. So what I'm saying now is sometimes called the Logos theorem. It should be called half of the Logos theorem. Okay, because it tells you that at the free level, the space of states is what you get from light cone quantization and has good definite, good inner product. This by itself, a real Logos theorem is that no unphysical states, no negative norm states appear as poles or cuts in S matrices. So the true Logos theorem is a proof of unity. As we heard from Ashok, while there are many ideas on how the proof of unitarity will work, because of IR divergences, there's never been a clean proof of unitarity of string theory. Okay? It's technicality, but an important one. Okay? So, I would say that you will only really say that there's a Logos theorem once you have a proof of unitarity within this data. In the sense that if you start scattering good things, but you produce bad things at equilibrium channels, you produce ghosts. That's not good. So unitarity completes the proof, which is not 100% done. But as we discussed in the course, more or less the ideas are in place. It's possible subtleties that we'll have to find. Okay. Other questions or comments? Okay, so let's start with the discussion of the notes. Okay. Now, the kind of proof, there exists a proof, and the proof is the kind of proof that a mathematician would give. Okay? So you're going to have to suspend disbelief for the next 20 minutes or so. You're going to have to stop yourself from saying, what are you up to? Okay. And you'll see by the end, but it'll take some time to see that. Okay. So the first thing we're going to do is to do the following. We take space-time and we divide it up into, time to 25th direction and 1 to 24. Okay? So t plus x25 is is called x plus t minus x25 is called x minus. Okay, so we did, because we want to make contact with the light cone result, we'll use light cone times coordinates in space time. Okay? And correspondingly, okay, there may be some square root 2s, right? Okay, let's square root 2s. Okay? And correspondingly, we will define for the oscillators alpha plus minus is equal to 1 by square root 2 times alpha 0, so n plus minus alpha 12. Okay, Pushinsky equals 1. Okay, so at every oscillator level, we're just making a change in basis, right? A change in polarization basis. Instead of using Cartesian polarizations, we're using Cartesian Euclidean 24 dimensions and plus minus. This is clear? Okay. Now the next thing we want to know is what the commutational relations are of these guys. Okay? So let me write them down and then we'll see if we believe them. Alpha plus m, alpha minus n is equal to minus m delta m minus n. And alpha plus with alpha plus is equal to 0. Now, why is this correct? Let us remember in an ordinary we had alpha mu m, alpha mu minus m minus n equal to eta mu times delta of m times f. Right? This was the commutational relation associated with positive guys being annihilation and negative guys with creation. So annihilation to complicate creation is a positive. You see here. Provided we use the space-like indices. But for time-like indices, because by Lorentz invariance of eta mu nu, it goes the other way around. Okay. So now let's look at this alpha plus and alpha minus. Let's look at alpha plus. Alpha plus, alpha plus. You get 0 with 0. So alpha plus with alpha minus. And 25 with minus 25. Both of them come with a factor of half. So you get a minus sign from the zeros because the metric was the opposite sign, and a minus sign for the 25 because that came with minus. Is this clear? Okay? So this computation definition is correct. Okay. Now the next thing we're going to do is to define n light cone to be the following. 1 by m alpha plus minus m m runs over all integers, positive and negative, but not equal to 0. Now, what is this operator? You see, because So what's this operator? This operator counts the number of plus oscillators minus the number of minus oscillators. Let's check that. Okay. Suppose I take n light cone, I mean up to some overall say. Suppose I take this guy acting on alpha minus k plus on 0. Okay? The only way this guy will click, I suppose this is normal object. We'll talk about it. Right. So the only way this guy will click is if this fellow was K. So this contracts with this. Okay? And if that fellow was K, we will get the commutator of alpha minus n with alpha plus, which is plus n. Wait a minute. I may have set the clock. Let's work out what the other guy is. I think alpha minus m with alpha plus n will also be equal to minus n delta m minus. Because of the same. You see what I mean, right? Flip these two, you get a minus sign, but with a minus n, with an n, but n is minus n. Could be one. Okay, so but that's the point. Okay, so let's suppose we act with this. Let's seriously calculate this. So we got alpha minus m, alpha minus k. So the only way this clicks is when we replace this by the commutator. The commutator will give us, it clicks when m is k, so we get minus k, but m was k by k, times alpha plus minus k on 0. Okay, so this is equal to minus alpha plus minus k on 0. On the other hand, suppose we act with this on alpha minus. This room is booked from 2:30. Okay, let's keep going first. Okay, suppose we do alpha minus k. Okay, suppose we looked at alpha minus k of minus on 0, and we acted with this guy. Okay, now what will click? When this guy is plus k. Okay, so m has to be minus k. The commutator part will give you the same. Will give you a minus k, but the same was minus k. So now in this case, by acting with this, we will just get plus alpha minus minus k. You see, because this relation didn't care about whether you had plus or minus first, so we did. Because this relation didn't care whether you had plus or minus first. The commutator part just goes through. But the point is that in one case you had m equals k, in the other case you had m equals minus k. Right? And now you can easily check for yourself that acting in a string of oscillators, say 2 alpha minus oscillators, you would get 2.
Because all of these oscillators, all of these will come specifically.
Exactly, you just keep building the contractions. generator that counts total number of the way I've written it, total number of minus oscillators minus total number of plus oscillators.
But it does not say anything about the levels.
Yeah, it doesn't care what the level is. Because every level, the k is cancelled, the magnitude of k cancels. It's total number of oscillators minus total number of oscillators. Now, plus and minus are Euclidean sort of Lorentzian versions of of plus and minus in complex coordinates, right? So on a plane, suppose plus is things moving that way, minus is things moving that way. If you count the total number of plus oscillators minus total number of minus oscillators, what will you be counting? Angular momentum. Each oscillator, no matter what its level, carries angular momentum plus 1 or minus 1. Okay? So this is sort of like that. This is almost the generator of Lorentz transformations. The thing that stops it from being the generator of Lorentz transformations is that we have only included the contribution of non-zero modes. Non-zero modes. There is a part, the true generator of Lorentz transformations of the matter, the probability field theory, includes a part that has contributions of zero modes. And we'll ignore that. Okay? So it's almost the generator of Lorentz transformations up to zero modes. It's the oscillator part of the Lorentz transformation derivatives. Okay? Great. So we understand our NLC very nicely. Now, what we're going to do is to ask, suppose you take a BRST charge and you break it up into parts which have definite quantum numbers under NLC. Okay? That is, you take the BRST operator and you do commutator of NLC with BRST, it will give you nothing particular. But that's because the BRST operator can be regarded as a sum of 3 terms, or sum of some number of terms. 3. Each of which have definite charge under NLC. Now, let's think about that for a minute. The BRST generator has parts that come purely from hosts, okay, which are totally neutral under NLC, because NLC is just acts on the matter. Okay, so the only term that we should worry about is, so most of the BRST charge, the part that comes purely from hosts is NLC, has NLC charge 0. What about the part that comes from C times L? Okay, L itself is Lorentz invariant. So L0 itself has an alpha plus with an alpha minus. The only way we can get a non-zero charge is if one of the alphas was alpha 0. Because the charge of alpha 0 is not counted by this operator. So you say that every term in L0 or every term in L that lacks an alpha 0 is automatically NLC 0. Because it will come with a positive, with an alpha plus and an alpha minus. Okay? On the other hand, terms which have NLC, terms that come with the 0 mode can carry NLC charge, in fact do carry NLC charge. And in fact carry NLC charge at most either 1 or minus 1, because it's at most an imbalance of one such as oscillator.
There's a 0 mode you're talking.
Yeah, so there are terms in, let's say, so Q is Cn L minus n. The term in L minus n that has the 0 mode will come with an alpha 0, alpha minus n. That piece, and only that piece, carries some charge. Now, depending on whether that n was positive or negative, and whether we take the part with the plus sign or the minus sign, we get charge 1 or minus 1. Is this clear?
This last one.
Okay. Yeah. See, suppose we take the term Cn element. Okay? So Cn carries no NLC number, it's purely ghost thing. It's all in L minus n. L minus n, what's its structure? Alpha mu m alpha mu minus n minus m. Okay? Now, we move to this line code basis. One of these is a plus, the other is a minus. So if we don't take the zero modes, if we don't take the zero mode contribution here, this thing is just zero.
In the light one when you do, it's we are not taking the zero mode into account, oscillators.
What do you mean?
I mean, when you rewrite this aliens in the light cone, say in oscillators.
By light cone, all I mean is I'm going to this plus minus basis. All modes are there. Zero modes are there, as well as non-zero modes. You remember our expansion of L, right? It included a term with oscillator number 0. Is this clear? Okay? So only those terms which include oscillator number 0 will carry charge. Such terms are imbalanced by exactly 1 unit. Because they carry exactly 1 oscillator. Okay? Whether the sign is plus or minus, you have to look in more detail. Some terms will carry plus 1, some terms will carry minus 1. But it's clear that you'll only get charges 0, 1 or minus 1. Is this clear?
So L minus n has decided two set terms where alpha 0 comes with plus or alpha 0 comes with minus.
Yes.
And one will have a plus 1 charge, other will
Exactly. Okay? So the full PRST chart, we'll have to stop soon. Nobody is disturbing us. But I have a Skype conversation I'm going to do. Okay. So we have Q as Q1 plus Q0 plus Q minus 1. Where I just decompose the BRST charge into its quantum numbers under NLC. Okay. Now, as we've seen from this discussion, you're seeing that while Q is a complicated operator, Q1 is a very simple operator. Right? Q1 comes entirely from Mangesh set. Either K is entirely proportional to either K plus or K minus. If you think that through, and then is bilinear with one matter oscillator. So let's say we're working with a given momentum sector. So alpha 0 is a number. Okay. So it's bilinear with one momentum generator, one matter oscillator, and one ghost oscillator, and one C oscillator. Okay. So the strategy that we're going to adopt. Let's quickly. Let's see if we can proceed and complete this call. Okay. So this is very nice. So we got this Q1, and we're going to try to compute the cohomology of Q. Now, in the last lecture, in response to the question by Arunabha, you remember that I told you about this nice thing that cohomology is in one-to-one correspondence with harmonic states. Once you define an Hermitian quantity, what we're going to do is to more or less implement that. Okay, so what I'm going to do is to define an operator which sort of plays the role of the Hermitian conjugate of this in some definition. So we're going to be like that, like Q1 diagram. Okay, I won't call it that. Some operator which I'll just define. Minus sign. Okay, you see what I've done? There's some irritating prefactor. I divided by that irritating prefactor. So that when you take commutator, for instance, prefactor will go away. That's just convenience, it doesn't do anything. Okay? But the main thing that I've done here is I've replaced this guy with the Hermitian commutator. Okay? So if I take the dagger of this, I would get alpha n b minus n. Since I'm summing over all n's, the minus is going to matter. That's what I do. Okay? So roughly speaking, I'm dealing with a Hermitian conjugate up to some normalization, which is I'm choosing for convenience. Up to normalization, the two operators I'm looking at are Hermitian conjugates. Is this clear? Is that clear? No. Okay. And now what I do is to define the operator S, which is Q1 anti-commutator. What are we doing? We're just paralleling our discussion of, you remember we said d star plus d star d was del square. The zero modes of this guy are one-to-one correspondence cohomology. Okay? I'm just building that operator. Okay. Fine. So S is this chap. S is this chap. And now we can just compute what S is. Because we've got an explicit expression. Okay, I'm going to give you a result. And then we'll see if we find it plausible. Okay. NBM is the operator that tells you how many oscillators at the emitter level of the BCFT are excited. B being fermionic, the answer is either 0 or 1. NCM is the operator that counts how many levels of the CCFT at level n is excited. C being fermionic, the answer is either 0 or 1. And N plus M is the operator that tells you how many oscillators at the emitter level of the plus oscillator, the light cone plus oscillator, are excited. Light cone plus oscillator being bosonic, the number ranges between 0 and infinity. Okay. Similarly, N minus M is the operator that counts how many oscillators of the minus oscillator are excited. Alpha minus being bosonic, number ranges between 0 and infinity. Okay. Now how do we? So firstly, what are the formulas for these things? The formula. This, if you wrote this in terms of formulas, this would be M B minus M CM.
Is this?
What? No. Yeah, this is S. Okay. Plus C minus M BM. Okay. Plus alpha minus M plus alpha M minus. Plus alpha minus M alpha M. Maybe I got some sign. But you understand, right? These will be multiplied by M because that's intent level. These would not be multiplied by M because the commutation relations automatically have an X. And we have got the sign. The sign maybe. Okay. Now let's see how we would get some formula like this. This guy and this guy just cancel with each other. Okay. So everything that you get will be with commuting this. So for instance, you could in the commutator you could commute this with this. This will give you a BC term. Okay. The commutator has a factor of m, so you get m times BC. Claim as you get this. Okay. Or you can commute the C with the B. If you did that, you would get alpha plus, alpha minus, alpha minus, alpha plus. Okay, so these now run only over positive things. I mean, these two are equal. If you sum over all integers, here I'm summing only over integer. That was one treatment. Okay, do you agree that it's plausible that we get this? Can we go ahead without algebraically verifying? Okay, excellent. So now let's take this in words. What do we get? We get that this S is a positive definite operator. Why is it positive definite? Because it's a sum of numbers weighted by integers, all of which are positive. Okay, so this S has a zero mode sector. What's the zero mode sector? The set of all oscillators that have no B excitations, no C excitations, no plus excitations, no minus excitations. What is the other name for the set of all oscillators that have no B, no C, no plus, no minus excitations? Hilbert space of light cone gauge. Because that's what light cone gauge quantization gave us. Only the I oscillators. So if we can show that the cohomology of Q is simply those states that are annihilated by S, of Q1, then we have shown that the cohomology of Q1 is the light cone gauge Hilbert space. Okay? Now the analysis we did the general analysis we did last class almost does it. But let's read it. Okay? So what I want to show is that the cohomology of Q1 is the zero mode space of S. Is this clear? The key point is that Q1 the key point is that Q1 commutes with S. How do we see that? Well, let's look at the formula. The formula for Q1 always has one destruction and one creation. The formula for S counts all oscillators evenly. So if it destroys something at level M, it creates another thing at level M, it doesn't change the S value. It doesn't matter whether it destroys the C and creates an alpha minus or whatever. Okay, so it's clear that Q1 commutes with S just from the explicit formula. Is this clear? The argument was that S was the operator that counts total number of oscillator numbers at any level. Whether it's B, C, plus, minus, we don't care. Okay? So we want to see whether the total number of oscillator numbers is preserved by this thing. So this is one destruction of one creation, therefore, at each level. It preserves total number of oscillators. Okay? So Q1 commutes with S. So that's sort of nice. Now, see. Suppose we also can see that S, is a commission operator whose eigenspace is every integer. Or his eigenspace is it's every integer, but anyway, integers. Okay? So S on psi, we can work in a basis where S on psi is equal to S on psi. S running from 0 to infinity. Okay. Because Q1 commutes with S, the question of cohomology can be broken up little s by little s. We've been through this before. An operator commutes with an operator like this one. Okay. At each eigenvalue, we've got an independent cohomology question. Okay? So first let's compute the cohomology of Q1 in the eigenspace with S not equal to 0. No matter what it is, some S. Okay? So suppose we got some psi such that S on psi is equal to S times psi. Okay? And I have Q1 on psi okay? I have Q1 on psi is equal to 0. Therefore, it follows that R times Q1 on psi is equal to 0. But we know that in this space, Q1R plus RQ1 on psi is equal to S psi. But RQ1 on psi was 0. And therefore S times psi was equal to Q1 of R psi. And therefore psi was equal to Q1 by S of R psi. And therefore psi was exact. Is this clear? So in the eigenspace with some non-zero s, it doesn't matter what, every Q closed state is automatically Q exact. What? Q1 closed state. Remember our strategy. Our strategy is A, to find the cohomology of Q1, B, to show that the cohomology of Q1 is isomorphic to the cohomology of Q. We're pursuing strategy A. Okay? And therefore we have shown that here in this, in the space of non-zero cohomology, non-zero eigenvalue of S, the cohomology of Q1 is empty. There is no state that is both Q1 closed. That is Q1 closed, that is not also Q1 exact. Okay. Now let's go to the 0 points. What about S equals 0? You see what? We can't play this argument at S equals 0 because at S equals 0 we just get 0. And so we conclude that Q1 times R on psi is 0. And that's great, but what have we learned? We've not learned that psi is exact. Okay? Now I want to show that that suppose we are at S equal to 0. Okay? That or I want to show that all states at S equal to 0 are both Q closed as well as Q exact. Okay? And the proof is very much like what we had for the tachyon. Because at S equal to 0, you can, because the action of Q1 does not change S. We just work at S equal to 0, calculate what happens when you have Q1 on any S equal to 0 state, and you see what you get. But the point is that we always get 0. Because S equals 0 is those states that have no oscillators that are either plus or minus or C or B. So S equals 0 is the light cone Hilbert space. It's the vacuum times arbitrary oscillators in the alpha 20, the 24 spatial direction.
S equals 0 is just the oscillator numbers will cancel each other.
No, there's no cancellation. It's all positive. These are numbers. Okay? So S is equal to 0 is simply those states that have no plus oscillators, no minus oscillators, no B oscillators, no C oscillators. It's the only way you can have S equal to 0. Okay? But if you have none of these oscillators, then clearly every term by term, every term here annihilates the state. Because one of these two is always a destruction. And therefore Q1 annihilates all states at S equals 0. Clear? Therefore, all states at S equals 0 are annihilated. Therefore, they're all Q closed. Moreover, there are no Q exact states at S equals 0. Because if there was a state, since Q1 doesn't change the S number, if there was an exact state S equals 0, it would come by Q1 acting on a state at S equals 0. But Q1 acting on any state at S equals 0 to 0. And so we've concluded that there's no cohomology at S not equals 0. And every state at S equals 0 is a cohomology. Okay? And so we've concluded that the cohomology of Q1 is precisely the same as the set of states that have S equals 0. Okay, we knew this, okay, because in response to Arunabha's question last time, we had discussed this in some general. If you believe the claim that this is, that up to details that don't matter, this is the Hermitian conjugate of that, this is simply the same state that cohomology is one-to-one corresponding to the harmonic states. It's a statement very familiar to anyone who knows some differential. We're just mimicking that analysis. Okay? But the thing that was really nice was that the harmonic forms were so simple. They were the states with no plus, no minus, no B, no C. Oscillators. In fact, they were the Hilbert space of light components. Is this clear? So we have completed part 1. Part 1 was to demonstrate that the cohomology of Q1 was the Hilbert space of the light. In fact, yeah. Now, part 2 is to show that the cohomology of Q, okay, is the same as the cohomology of Q1. Now we have an option of doing this today or next class. You guys can get to choose. Next class.